Hi everyone, so in this video I'm going to explain the concept of mobius function and Euler's phi function. So giving the brief concept of mobius function first. Mobius function is denoted by mu n. Alright, now whenever you have, since we know that every number, n denotes the numbers set of integers, we know that n is either prime or product of primes, right? So if n is a product of primes, if n is the composite number and have factors, distinct prime factors. So at this case, we take that how many distinct prime factors are there? We square that number of prime, square the -1 with the numbers. That is, if I conclude mu of 6, so the prime factors of 6 is 2 into 3. So we have two distinct prime numbers. So Mobius function says that mu of n equal to -1 of k if there are different primes. Prime are distinct in this case, distinct. So for mu of 6 we have two distinct primes, so -1 per 2, we get mu of 6 equal to 1. Alright, now one more thing that we have a property, this property 1, we have another property, that is, it says that if the n can be represented using a product of have one of the factors in the n is square factor, then we get that mu of n equal to 0. For example, if you take 4, so for 4, the product of prime factors of 4 is 2 squared. So we have the square factor in the in the primary prime decomposition of 4. So mu of 4 will be equal to 0. So these two conditions, these two properties we have, and also we know that mu of all prime numbers 3, mu of 2, mu of 5, they all have only one prime decomposition for that, -1 power k equal to 1. We have -1 power k equal to 1, -1 power k equal to 1, because phi has only one prime factor, that is 5 itself. So from this we get equal to -1, -1, -1. So these are pretty much about the Mobius function. If to be precisely speaking, there is a function which is mapping from n to r, alright, or maybe n to c. You can consider both real numbers and complex numbers, which is defined by n of n equal to n. You can go through the definition which is given in your book. Alright, now there is a theorem related to Mobius function, that is summation of mu d, that is summation d divides n mu of d equal to 1 by n if n equal to 1, 0 if n is greater than 1. There is a summation mu of d. For example, it says that basically what is happening here, this is summation of fd. We are considering the sum, so the sum of numbers which divide this n. They are the different numbers which divides this n. For example, if I consider a summation d divides 6 of ft, so you can write it as f of 1 plus f of 2 plus f of 3 plus f of 6. Alright, so and then we can have this 1 plus 2 plus 3 plus 6 equal to 3 plus 3 is 6 plus 6 is 12. We get 12. This is the sum of divisors of 6, but instead of this fd, what I am doing is, if I will apply mu of d to that, summation d divides 6 mu of d, at this moment I will get mu of 1, mu of 2, mu of 3, mu of 6. Alright, now we know that the mu of 1 is 1. The case is trivial. In this case, one more property of mu of is that mu of 1 will be equal to 1, and mu of 2 equal to 1, because it is only one prime factors in a prime decompositions. Minus 1, we have mu of 6, we have already done this, mu of 6 equal to 1. Alright, from this 1 and 1 will get cancelled, 1 and 1 will be cancelled, we get 0. Alright, now what it says that this condition here, this condition holds right over here, that is 1 if n equal to 1, 0 if n is greater than 1. So we got the n which is greater than 1, that is we got n equal to 6 right over here, which is greater than 1. So from this we can say that we got the 0. So the theorem says that now we are proving that actual theorem for it. Now it says that 1 if it equal to n equal to 1, then 0 if n is greater than 1. So now proving the theorem. Now if n is 1, then the both left hand side and right hand side will be equal to 1. So we are assuming that n equal to n is greater than 1. So n can be represented as product of primes with p1 alpha 2 so on pk alpha k. Alright, now these are the primes. From there, this mu d is not equal to 0, for d equal to 1. These are distinct primes, right? Alright, so we have to consider this mu of d divides n. So we don't know, there are n numbers, k numbers of primes. So now we are writing mu of 1. Alright, that is what we did previously, mu of p1, mu of p2, all possible combination, mu of pk, and then for multiplying this p1 with p2, p3, p4 so on, you will get mu of p1 comma p2 so on, and also you will get mu of p1, p2 so on pk. Hence we get this at the end, we get this mu of d, because at the end we get n. Alright, the previous problem that we have got in here, at the end we get 6, which is equal to this n that we have selected previously. Now also we got this n, which is equal to this n. Alright, at the end. Now mu of 1 is 1, we know. Alright, k means product of primes here, k c1 minus 1. We don't know how many primes are there. Alright, so we are just multiplying with k with minus 1. Alright, so that it will act accordingly, plus kc2, the product of these two types of primes. Alright, from this we get minus 1 whole square. Alright, and so on, kck for this one, minus 1 power k. Alright, k times distinct primes, so hence minus 1 power k. We don't know how many primes are there, that's why we put minus 1 power k. Now from this we can get 1 minus 1 power k. Alright, we get 0. So this is the pretty much theorem says that and that's proof. That's proof mu of d divided n mu of d equal to 1 by n, such that 1 0 if 1 if n equal to 1 if n is greater than 1. Alright, now in this case we got 0 because we assume that n is greater than 1 in the beginning. So this is a theorem that it's pretty much about the theorem of a Mobius function. Now we are moving on to understand the concept of Euler's phi function. Alright, now we are dealing with Euler's phi function. It denotes with phi of n. What it says is that it counts the number of primes, or the if you select a number n greater than or equal to 1, right, it will count how many primes, how many numbers lesser than this n are co-primes with this n. Alright, so for example, if I consider 3, the numbers which are lesser than 3 are 2 and 1, right? So how many primes there are actually co-prime with 3 is that 2 and 3 have 1 as a common multiple, that is GCD of 2 and 3 is 1, so we consider this as co-prime. 1 and also 3 is also considered to be co-primes. So how many co-primes that we got is 1 and 2. So phi function of 3 equal to 2. So by this we can conclude for every prime numbers we have number of co-primes which will always be lesser than 1. That is, so from there we can generalize that phi of n will always be equal to n minus 1. Alright, now if I consider phi of 6, and we know that 6 can be written as 2 into 3, and from this we have to check the GCD of 2 and 3 is 1, right? There is a property that I'm going to discuss afterwards, but for now I'm just telling you that 6 equal to 2 into 3, the GCD of 2 and 3 should be equal to 1, sorry, the both should be co-primes. Then we can from there we can write phi of 6 equal to phi of 2 and phi of 3, we will get 1 and we get 2, that is phi of 6 will be equal to 6. Now we haven't discussed this particular property yet, but I'm going to use that afterwards. Why we have to deal with the 2 comma 3 equal to 1. Alright, so if you don't get this 2 comma 3 the co-primes, then you won't get the result, because this phi function is not completely multiplicative. That is, we are going to discuss afterwards, but for now just keep that in mind. There is also I'm going to give you another example, phi of 4 for example. That is how many primes which are co-prime related to 4 and which are lesser than 4. That is 1 which is relative to 4 co-prime, 2 is not a related to 4 because there is a common factor between 2 and 4 is 2 itself, so 2 cannot be a co-prime. 3 can be co-prime for 4, so then we have 4. So there are how many numbers are co-prime to 4 is 2, 1 and 2. So phi of 11, this is the prime number, you get 10. Alright, so this is very easy, right? Phi of 10, if I consider phi of 10, you will get 4. You can find it by yourself, count it. Now what if the numbers are big, large numbers, for example phi of 2, 3, 4. Oh, how do you find this? Can you be able to find that? Actually, there's a property or the methods to get the answer for this. That is, we have the formula for that as well to find out the phi of 234, and also you can, if you can split this up 234 and get this done, if the products that you're getting, the prime decomposition of 234, if you get this co-primes in the product decomposition, then you can find it easily if you split it up. Alright, I'm going to discuss that formula as well afterwards, and also how do we get and also I'm going to derive the formula for that, derive the formula as well. Now for now, this is pretty much about Euler's phi function. We denote it with phi of n. Alright, phi of n. Now there is a theorem related to this Euler's phi function. Previously we done the theorem for my mobius function. Now we are dealing with the Euler's phi function, and the theorem, it says it is pretty much similar, looks similar actually. Summation d divides n, the same thing that we are using, phi of d equal to n. If you consider number of divisors of n, and if you add these divisors, you will end up having n equal to n. For example, considering this, alright, this is simple. The theorem, it says that summation 5t equal to n, summation 5t equal to if d divides 15, we get equal to n. So we have to prove that only. Alright. Before that, I want to give you some basic concept, that is, if m comma n, the GCD of m comma n is equal to t, you can always divide this GCD by you can always divide this m by d and n by d and d by d. You will get this. Alright, keep that in mind. We are going to use that. Alright, now I will wait for some time for a break, because I'm recording this constantly for 2 hours now. I will take a 5-minute break. I'm just pausing the video. We'll continue it. So alright, I'm back. Okay, so what you have to do is this, in this theorem, if n equal to 1, then the theorem is trivial in this case, because we know that phi of 1 equal to 1. So we are assuming that n is greater than 1 for this theorem. I'm speaking about this theorem right now. Okay, so and for this, one more thing that I want to add up over here is that we have to use a set basic, that is, for s is equal to 1, 2, 3, 4, 6, we will be having set s1 k belongs to s, set that k comma 6 equal to 1. Sorry, this s1 s2 k belongs to s, set that k of 6 equal to 2, because GCD of 2 and 6 is 2. Alright, S3 we get the same thing, that is equal to 3, and S4 we get K of S equal to 6. Alright, S is in the case of in this case we have S is equal to 6. Alright, so these are the sets which we got by having the GCDs of numbers which can divide the 6. Now what you have to do is you have to consider this set S equal to union of these SDs where D divides N. Alright, S is equal to union of SDs. Now there is M, this is a set SD, there is some M belongs to this S, alright, such that M comma N is equal to D, the GCD of M comma N equal to D. We don't know the set M, the value of M, hence the GCD of these two also unknown, so we are generalizing. So for that reason M belongs to S and the GCD of M comma N equal to D, the same concept that we are using here. And we know that we can represent this as M by D and N by D equal to 1, right, where M belongs to S, and we know that 0 is less than or equal to M by D is less than or equal to N by D. Now M can be written as this M belongs to S, M equal to M dash D. M can be written as M equal to M dash D because D is a GCD and D is dividing this M where M belongs to S, alright, such that 0 is less than M dash is less than N by D, and also N by D comma M dash, the GCD will be equal to N by D N dash this N by D equal to 1. From this we get that the number of elements in the set S SD is equal to the number of elements in the number of elements in it, that is M dash, and that is what we have assumed, that M dash is the number which divides SD, and from this we can conclude that this SD is equal to the number of M dash which are relatively prime to N by D. That is, from that we can say that phi of ND will have phi of N by D elements, alright. From this we can conclude that the number of elements will be equal to phi of N by D, where D divides N is equal to number of phi of D's, because N by D, since D divides N, we can write phi of D. So this is the theorem. Or else you can write it as this, S is equal to union of SDs, right? Just adding mod for positivity, because we have got this number of sets that is equal to N. As we know that D varies from among the divisors of N, so we get this N by D, alright. From this we can get just replacing this N by D with D dash, putting N equal to D dash From this we get this is the theorem. I don't know if I'll be able to explain you correctly or not, but we got this. Alright, now you can refer the example. These are the S values, that is we have here 1 2 3 4 S we have got, and from this we get this 1 3 and 5 and 15. If we have this phi of d, we get this equal to the sum of d's equal to number of d's, sum of d's equal to number of d's. From this we get sum of d's equal to number of d's. That is from this we got, as you can see, we have got n by d comma m dash, this the GCD of m by d and m dash equal to 1, and this m dash is dividing this m. From this we can conclude that number of these are equal to sum of these are equal to number of sum of these are equal to the number itself. So by this we have done a theorem, which is a basic theorem which is related to Euler's phi function. Euler's phi function. Now one more theorem that is that which is a relation between this Mobius function and Euler's phi function. We will discuss that one also. That is, it says that phi of n greater than summation mu of d into n by d. Alright, okay, actually there are two ways to explain this relation between this Mobius and Euler's phi function. One is using the product formula of that is n equal to prime numbers, where we can use this Mobius phi and phi relation and can get this relation by using that. I will explain both methods. Which one is easy for you, you can follow that, right? Alright, from the definition of Euler's phi function, for phi 1 equal to, you can write k equal to 1 to n, you get 1. This represent k comma n equal to 1, the GCD of k comma n equal to 1. So from this we can write, as the GCD of k comma n equal to 1, we can use this, that is phi of n can be written as k equal to 1 to n 1 by n comma k. Since the GCD of n comma k is equal to 1, then it will become this one. Alright, now the summation is running over 1 to n, and also there is a d. The d we are generalizing, as we know that, where this d is the GCD of n comma k. So replacing this with that, phi of n, and summation is adding to add up all the divisors of n comma k. Alright, 1 to n, and this summation which d divides n, also d divides k, basically d divides n comma k. So from this we can have mu of d. Alright, we got mu of d from this because mu of d will be equal to the number d itself. Alright, the GCD itself, hence the summation of mu of d will be equal to the number itself. From this we can get phi of n is equal to summation mu of d, where d divides n, where we are considering that d divides n, and summation q equal to 1 to n divides d into 1 Now since d divides n, we can have d divides n mu of d, we can have n by d. That's it. These are relation we can have, or else you can use, okay, I don't know if I cover the entire page or not, but yeah, so using 1 over here and replacing with some nk with a GCD of 1, that's what we believe, and then we are just multiplying this 1 with the d, and after this d is getting multiplied with both sides, we can have k by d and n by d, which will be equal to 1. So this is what I got, that is d divides n, d divides k, that is mu of d, that is summation runs over all the numbers, which divides d with the mobius function, and we have considered this 5n, that is Euler's function, and we got this mobius function, though we got the relation between this and this. And one more way that we can represent this is, before understanding that way, you have to understand this. N can be written as, n is a composite number, and it can be written as this product of primes, right? So we have already seen this, how we got this. So n is a composite number and it can be written as product primes. Now phi of n is used to calculate the phi of n is used here to find the relation over here, but before that we will get we are basically finding this the Euler's phi functions of n, basically this, but we know that this can be written as p1 k1 minus p1 k1 minus 1 into p2 k2 minus p2 k2 minus 1, so on, pr kr minus pr kr minus 1. Alright, so if you just check out this separately, pr power kr, you will end up having the same thing. Alright. Okay, so phi of prime numbers, we know that you can get it from here like this. Maybe I haven't shown you previously, that is, if you consider phi of some 4, this will be equal to 2, right? Because there are two numbers which are basically co-prime to 4, so we know that, right? That is, those are 1 and 3. Now you can also calculate this by using the method that we have here, is that 4 can be written as 2 square. So phi of 2 square can be calculated by using the method that we have here. 2 square minus 2 power 1, that will be equal to 4 minus 2, that will be equal to 2. So you can do this for every number. That is what we are doing right over here. So we have p1, so we are finding the phi function for that. Alright, you're just having a phi function both sides. Now for each and every term you got it. Then from this you can have p1 common, and you will be left with 1 minus 1 by p1 into p2 k2 comma 1 minus 1 by p2. From this you will get pr common, pr power kr common 1 minus 1 by pr. Alright, from this you can write p1 k1, taking this together, p2 k2 so on, pr kr into 1 minus p1 into 1 minus 1 by p2, so on 1 minus 1 by pk pr sorry pk pr sorry not pk. Now this right over here is equal to n, and this right over here is equal to product of p divides n 1 minus 1 by p, where p divides this n, because these are p numbers, these prime numbers are dividing this n, so we got this product of p divides n 1 minus 1 by n, and we have got phi of n. Alright, now we can have a relation, that is we can add the relation of Mobius function to this. Alright, we got this right. Now what I'm trying to do here is that sending this n to that side, phi of n by n. Alright, from this I can write the same thing, just elaborating again, that is 1 minus 1 by p1 minus 1 by p2, so on, minus 1 by pn, all the combinations, 1 by p1 p2 plus so on, plus 1 by p1 pn minus 1 by p1 p2 p3 plus so on. You will go up to minus 1 power k into minus 1 power k by p1 p2 so on pk. This much times you have to do. Then you know that Mobius functions, whenever the primes whenever the number have a square factor, the prime decomposition of a number has a square factor in it, it will become 0, and if it has distinct primes, we have to use this mu of n equal to minus 1 power that number of distinct primes k, distinct prime factor, that is k, minus 1 power k. Alright, so from this we can have mu of 1 is 1. Alright, basically applying this mu to this function, right side function, we get mu of 1. Let me write in mu of 1 plus mu of p1 know that mu of 1 equal to 1, this will be equal to minus 1 mu of 1 p1 plus summation of 1 by p1 p2 minus 1 by pi pj ps distinct primes, and minus 1 power k p1 p2 so on pk. From there we can have summation d divides n mu of d by d. since we got d from d, mu of d by d, we are adding all these, so summation for that. Now this is equal to phi of n by n. Sending this n back to again right hand side, you will get n into phi of d by n mu of d by d, or else you can write it as like this: summation d divides n mu of d n by d. So this is what we got, the relation between Mobius function and Euler phi function. And in the next topic I'm going to give you the formula for a Mobius function that we have already discussed over here. That this is basically the formula of Mobius phi function for to find a value for phi of any number n. So actually I'm not going to discuss that, but I will give you an example for that. Alright, giving the example for that, that is, we have phi of n can be calculated using the function, the problem that we have, that is product of p divides n 1 minus 1 by p. That defines the p number of primes which is dividing number of p's which are dividing this n, and we are taking the product of all these. So basically from this we can find the phi function for 210. That is n equal to, we have phi of 210, that is equal to 210 into product of all these numbers, that is the prime decomposition of 210 is equal to 7 into 3 into 5 into 2. From this we have 1 minus 1 by 7, the same formula that we are using, into 1 minus 1 by 3 into 1 minus 1 by 5 into 1 minus 1 by 2. So for bigger number you can calculate, previously I said that how do you calculate bigger numbers if I give you bigger numbers. So you can use this formula to calculate that: 210 into 6 by 7 into 2 by 3 into 4 by 5 into 1 by 2. From this we can cancel out 3, 2, and then 2 will get cancelled out, and then we have 7 divided by 2 and 4 is divided by 7. We have 6, that is 2, and we have to multiply with 210. 7 3 is 21, 30. Now what we have, 30 can be divided by 5, 5 6 30, but we are left with 6. 6 into this 2 is got cancelled by this 2. 6 into 2 into 4, 6 2 is 24, 12, 48. Sorry, 6 into 2 is 12, and 2 into 4, 12 into 4 is 48. So this is the product formula for to find the Euler phi function. So this is easy, and we have already seen how you got this. If you want, I can explain that as well. We use basically to find out the product formula, that we use the Mobius relation, and this is pretty much similar. Both problems you can use either of these two conditions. Now in the next problem that we have here is that, okay, wait a minute, I will continue